second speaker today, Taormina, who is joining us from the University of Durham, and she will tell us about Mathieu Moonshine, quarter BBS states at the Kummer point and nearby.
Right, so, well, thank you very much to the organizers for the kind invitation to talk today. I know we have a mixed audience, and I hope I will not be losing too quickly too many people. And start by giving you a little bit the plan of my talk. I should say that this work is done in collaboration with the chairperson today, with Kathrin Wendland, and we have a long-lasting collaboration on this project of Mathieu Moonshine since 2010. And as you have already kind of understood from Jeff's talk yesterday, the problem is not solved, and it's incredibly hard to make progress at this stage. So this material that I'm going to present today is not solving Mathieu Moonshine. It sheds a little bit of a glimpse of a light, maybe, but in any case, I hope you will enjoy learning a little bit about the context in which this work is set. So I will start with a preamble and the motivation, and then set the scene, talking about several terms and jargons that we use in theoretical physics in this context. And then I will move on to the discussion of a special class of theories, which are called K3 theories, that I will define in a minute, and look at what generic and non-generic such theories are, and why it's important to understand a little bit more their structure. And finally, I will concentrate on a very specific class of K3 theories, which are called Z2 orbifold conformal field theories. That's a little bit of a shortcut because I really mean Z2 orbifolds of toroidal conformal field theories, but it's a little bit of a mouthful, and therefore I've decided to just write it like this and introduce in this context the action of an SU2 group that I call SU2 geometric here. And I will end by giving you a postulate and a little exercise for our number theorist friends there, because we need a little bit of help maybe to solve that. Right, so the paper that I'm really concentrating on is the first one listed there, which is called SU2 channels, the cancellation of K3 BPS states. But of course, it takes its ideas from the works before that, and in particular, the so-called symmetry surfing program that we initiated, well, almost 10 years ago. So my preamble is basically to throw at you a bunch of functions that I hope you will recognize, or at least some of them. And I'm starting with the upper Lurch sum, which is called mu of tau and z, where tau is, as usual, a complex variable with a positive imaginary part, and use the convention that q is e to the 2 pi I over tau throughout the talk. And z is a complex number. And we see that this infinite sum doesn't transform under the modular group as a Jacobi form, but if you add something real analytic to this, it does. And of course, this touches upon the beautiful work done in Sanders-Sweger's thesis in 2002. So this function has elliptic and modular properties that are summarized in the first box there. Now, Polishuk is actually the person that, to my knowledge, had worked out the modular transformation of the upper Lurch functions in 1998. It's at least where I studied that from. But of course, Sanders has done a good job and generalized many of the ideas. And at the same time, together with Semikhatov and Tipunin, we also derived the modular transformations, not necessarily of the upper Lurch per se, but of a certain class of characters that we were interested in at the time, super conformal characters. Right, now the next box is a bunch of functions, a family of functions, again of the two variables tau and z, and they can be written in terms of the upper Lurch sum written above there. And the first two, well, you count them as 1 and 2, but the last one is actually a family which is parameterized by a real number h, which has to be strictly bigger than 1/4. And altogether, these functions, as you will see through the talk, have a meaning in physics. Now note that if we were taking the lower bound for h, so h equals 1/4, then we wouldn't be having a function which has the properties that we want, really. That's written in red there in the bottom of the page. However, it provides us with a nice way to write formulas, if you want, because the characters that I will use, well, they're called characters, I haven't said that yet, but I will in a minute. So these functions chi tilde r tilde, if you look at the value of the parameter n plus 1/4, then you can write it nicely as q to the n times this function that I have in red there. And I'm going to use this kind of notations in the talk. So why do I give you these functions? It's because there is another function, yet that's the last one I introduce here, which for the moment we call ECFT with an index 2 up there, which is actually a particular combination, linear combination of these functions that appeared in a second box in the last page. So 20 times the first one minus 2 times the second one, and then an infinite sum over integers, positive integers, of the third function that I showed you in blue, and coefficients an, which happen to be integers. And these integers actually a priori are just random, or they were in 1989 when we cooked up this function. But it was realized in 2010 by Gucci, Oguri, and Tachikawa that actually these numbers were dimensions of representations of a sporadic group, which is quite huge, which is Mathieu 24, M24. So 90, for example, is the sum of a 45 and a 45 complex conjugate representation of that sporadic group. So it's a finite group. It has 26 conjugacy classes. This is an infinite sum. So therefore, after a little while, you get representations which are not irreducible anymore, but they are sums of irreducible representation of M24. And mathematically, this has been proven by Terry Gannon in 2016, that actually we are talking about the group Mathieu 24 there. And because of this unexpected occurrence of the M24 into the story that we were developing at the time in the context of string theory, this phenomenon has been coined the Mathieu Moonshine. Now, I'm not going to go very much into Mathieu 24 here, but Jeff said a little bit about it yesterday. So it's a subgroup of the permutation group of 24 elements. It's a huge group. Its order is roughly 2 times 10 to the 8. So it's very, very large. And it's an important stepping stone to construct the monster group. Okay, so there's been a lot of activity around this in the 1980s and a little bit afterwards by Conway, but also Curtis and obviously Bob Grease, who constructed the monster group. In passing, I also want to relate the function that I define here as A of tau, which is the sum of A and Qn. I want to relate this function to a weakly holomorphic mock modular form of weight 1/2 on SL2Z, which of course is in the work of Don, just has the theory of these modular forms, as you know. And this is probably the first example in our field where we have such a modular form dating back then to 1989. So the question is, why is M24 making an appearance here? Now, mathematically, of course, it's just a fact, and you can go home. Terry Gannon has proven it, and okay. Now, if you know, and you will know a little bit more in a minute on how it came about, then it raises quite a few questions in string theory. So first of all, this function here, ECFT2 there, it's a weak Jacobi form of weight 0 and index 1. And it's a specialization of the partition function of a class of theories, which are called K3 theories, superconformal field theories. And not only it's a specialization, but it's an invariant over the moduli space of all these theories. So of course, when we have invariants, we should pay attention. And another fact which came about very quickly after the discovery of the Mathieu Moonshine in 2010 is that no one theory of the K3 type has M24 as a symmetry. So for physicists, this is a little bit destabilizing because we are used to look at partition functions and of course symmetries of the states that are organized, in representation of the symmetry group. Here, the symmetry, which is there, is at the level of a very specific specialization of the partition function, and it doesn't count the states with plus signs everywhere. There are signs coming in, and actually my talk is all about trying to understand what's going on when there are cancellations due to signs. Okay, so the working hypothesis for this talk is that there is a link between Mathieu Moonshine and K3 theories. Now, this is not established, and there are different schools. The other thing that I didn't write there is that we also believe that whatever has to do with M24 here in the string theory context is actually rooted in the geometric symmetries of the theory. Now, for example, in what Jeff said yesterday about the model that inspired this code developments there, he exhibited symmetries that went beyond the geometric symmetries of that particular, it was a K3 theory that he looked at, but he included more symmetries which come from strings. So already there, you could say that if we really want to understand M24, we have to go beyond geometric symmetries, but today we won't. So there should be a vertex operator algebra that underlies the Mathieu Moonshine. And therefore, this work could be viewed as a preparation for a construction of this VOA. Okay, and we expect this construction to be over the generic space of states of K3 theories. Whatever generic means, I'll explain. And in any case, if at the end of the day there is no connection with Mathieu Moonshine, it's still interesting to understand better these K3 theories, and in particular the generic properties. Right, so let us set up the scene for what comes afterwards. So I want to define what a K3 theory is, and for this I first introduce what a two-dimensional Euclidean superconformal field theory is, a unitary one. So it has the following properties. First of all, there is an n equals 2, 2 world sheet supersymmetry. Now the 2, 2 means holomorphic, anti-holomorphic, or left and right in terms of string modes of propagation. And if you have a string, then you have left movers and right movers. So that's the meaning of this 2, 2 there. And you have two types of supersymmetry on the world sheet, so two-dimensional surface that is swept by a string when it evolves in space-time, and therefore there is a background space-time there, and there is also, we also require supersymmetry on the space-time. Now, this theory comes with a central charge, which is a multiple of 3. Capital D here is a positive integer, and we will see that it relates actually to some geometry in a minute. Now, in the n equals 2, because there is n equals 2 Welsh supersymmetry, there is obviously an algebra underlying this symmetry, and it's a superconformal algebra with 2,2 generators, but there is a U1 Kac-Moody or affine symmetry in that algebra, and it's because of the presence of this U1 symmetry there that you have space-time supersymmetry, and this is linked to the phenomenon of spectral flow that I think everybody has heard about. Now, actually, the spectral flow exchanges the so-called Neveu-Schwarz sector and the Raman sector because the states there are space-time fermions, and in the space Raman here, there are space-time bosons. And therefore, the full space of states is the direct sum of these two sectors. Yeah? Now, the generators of the algebra I was talking about are more than what I've written here. Here I've concentrated on the 0 mode, because it's an infinite dimensional algebra, so we have many modes, but the 0 modes of the U1 in both left and right sector are called J0 and J0 bar. And then I have constructed a combination of the Virasoro generator, so which knows about the energy of the system, shifted by 1/2 of the U1 charge. Okay, all these operators commute between themselves. They are self-adjoint and diagonalizable. The spectrum of J0 and J0 bar are integers shifted by C/2, where C is the central charge. And these theories must, by definition, have a partition function in the Raman sector. Now, it's a slight modification with respect to the letter R here, because there is an extra little shift in the variables that you have to implement in order to go into this sector. It's called the R tilde sector. And this partition function in that sector, all right, the D here, now you see, refers to the fact that I have a central charge 3 times D. And I've written it in 2 different ways here. I've written it as a supertrace over HR of states. So we take the states which have these particular quantum numbers here. So Y here is linked to the variable Z of before in this way. Okay, and basically when we count the states there, we have to take the fermionic states with one sign and the bosonic states with another sign, and that's included in this notation S here. Now the second line there doesn't have the S because I've made it explicit exactly what I have to do in order to have my fermions and my bosons contributing with opposite signs. It turns out that it's linked to this -1 to the J0 minus J0 bar operator. Now, what else? I've gone from Raman to Neveu-Schwarz sector, and for this I've used spectral flow. As I said, it's present in the theory, so you can kind of torture the first formula a little bit and get to the second expression. Now, this partition function has elliptic properties, and also modular properties, and I've written them down here, right? The important thing is that the specialization of that partition function is now the function that looks very much like I wrote first in the first or the second transparency, except that now I've put a D here instead of a 2 because I'm a little bit more general, but very soon this D is going to become 2. And what we do here is that we actually project the trace here onto the kernel of the operator T bar zeros on the right-hand side, on the anti-holomorphic sector, let's say. So that's by definition what this function is, and it's called the conformal field theoretic elliptic genus. Now the fact that you can go and write from the first line to the second line is actually due to the supersymmetry in the theory. There are a lot of cancellation of states. And here, from here to here is because of all these minus and plus signs that come into the counting. There are quite big cancellations occurring. And what you really see in that function is the net result. And when you see the net result, you see what we call the generic states of the theory. So in a way, in certain theories, you have this extra complication here due to the cancellation. And there are some theories which don't have this complication. So we will come back to that later on. Right, so that function, which is the elliptic genus here, as I said before, is an invariant of these n equals 2,2 superconformal field theories that I was defining before. In passing, I also put here a little correspondence between the CFT elliptic genus and the geometric elliptic genus, the complex elliptic genus that was constructed by Hirzebruch and Witten in 1988. Actually, for X being the K3 manifold, for example, it is known that the two coincide. So you can view the elliptic genus coming from string theory, field theory, conformal field theory, or purely in terms of geometric terms, and it's quite a nice result. So we won't go into the geometrical part here, but the reason why this area is very rich is that there is a constant let's say, interface between geometry and conformal field theory. So a K3 theory now is a special case of this two-dimensional superconformal field theory. Now we take the central charge to be 6. So capital D here is 2. And capital D equals 2 is actually the complex dimension of a K3 surface, and that's linked. And the nicest expression that we can write for the elliptic genus is actually this ratio of squares of Jacobi theta functions here, or those depending on Z in the numerator and Z being 0 in the denominator. So an idea of why this is linked to K3, which is immediate from there, is that if you evaluate this at Z is equal to 0, you get 24, and 24 is the elliptic genus of a K3 surface, not the Euler characteristic, sorry, of the K3 surface. And this is not a coincidence, and there is more hidden into this expression when you expand in powers of Q. So we wrote in the first or second transparency an expression for this conformal field theory elliptic genus in terms of these functions that I constructed with Eguchi all these years back. So these, as you will discover, have a particular function here that we will discuss. So nonlinear sigma models on K3 surfaces are examples of K3 theories. I personally don't know any K3 theory which is not a nonlinear sigma model, but it's not proven. So never mind here, we will talk about nonlinear sigma models. So because of that connection with K3, you expect a symmetry here, which has 4 supersymmetries, so n equals 4, both on the left and on the right. And I've written here for you, just for the record, what the commutation and anti-commutation relations of these generators are. So these ones, L's, are the Virasoro generators. So this knows about the energy of the system. In blue, you have the generators of an SU2. Now, I should say that when we change the central charge and we fix it to be 6, there's something nice happening compared to a situation where it's not 6, is that the spectral flow generator that we had generically actually is enhanced because there are 2 more operators that have the right conformal weight to be considered as currents, as bosonic currents. And these 2 extra generators beyond the U1 are called J plus and J minus here. So, and it turns out that the structure that they form together is an SU2 affine algebra. So this algebra gets in the mix. GA and GBs are doublets under SU2. They are supercharges. They anti-commute. They have anti-commutation relations, to be more precise. And I've called the other pair of supercharges G bar here, but it's nothing to do with the anti-holomorphic sector. So the notation is not very good, unfortunately. And the little cartoon here tells you a little bit how you navigate a space of representation by acting with the 0 modes of this algebra. So suppose that you pick a state in your representation, then if you act on it with the ladder operator from the SU2, you increase the isospin, so the quantum number, by 1. And vice versa, if you take the lowering operator, then the isospin just decreases by 1. On the other way, if you act with the 0 modes of the supercharges in the Raman sector, we are here, then according to these relations, you increase the isospin by +0.5, which is here. Now, why did I write all this? I wrote this because if you now think that the state you're looking at is the highest weight state of your theory, of your representation, then by definition, any operator that is going to increase the isospin should not act. Otherwise, it wouldn't be a highest weight state. So you already lost J02 and J bar 01 acting, as well as, no, you lost G02 and G bar 01 and J0 plus, but you still have the G01 and the G bar 02 acting, as well as G0 minus. Now, there is a limiting case of this, because if you take the norm in the appropriate in the space here of the state G01 acting on the highest weight state, well, that norm should better be positive if we want a unitary theory, but it could be 0. And when the norm becomes 0, essentially you go from a situation where we have a massive representation to a massless representation. And this is basically the origin of this BPS jargon in this context, is that when you have a massless representation, actually, you have a shorter representation and you have BPS states that come in. So what do we do with all this? Well, we now can put our finger on these blue functions of the beginning as being actually the characters of the n equals 4 superconformal algebra that I just presented. And that's actually how we constructed them. So we knew of the n equals 4 superconformal algebra, and we looked for representation of that algebra, which are unitary. And that's what we got. So now we know that the elliptic genus in the context of capital D equals 2 can be decomposed in this sum of n equals 4 characters. Now, remember that was a specialization of a partition function. So here I define what I mean by quarter BPS states in this type of theories. So these are states which saturate the BPS band for half of the anti-holomorphic n=4 worldsheet supersymmetries, and which are massive with respect to the holomorphic one. So if you think of the little picture from the previous page, you see that that corresponds to what I tried to describe there. So on the left-hand side, so the holomorphic side of your expression, you have characters which are massless and massive contributing. But on the right-hand side, because of this projection, then you essentially have numbers coming in. So it's a drastic simplification. And however, these numbers should remember that they come from the fact that the representations are massless. And the quarter BPS states are basically contained, encoded into the massive massless part here. And they appear in these terms of the elliptic genus. So it's a fascinating story that could be told about what I have here in a dashed line, in dashed circle here. Nobody really understands what's going on there yet. So we will not talk at all about this sector, which has to do with the mass, the half BPS states, just not do that now, but look into the quarter BPS states. So as I said before, this elliptic genus counts BPS states with signs, according to whether they are fermions or bosons. It's an invariant on the moduli space of K3 theories in this case. And some of these K3 theories contain more quarter BPS states than others. So there are, in some cases, excess pairs of bosons and fermions. And that's where we are going. We want to understand that. So let us look at what we mean by generic and non-generic. So in a generic nonlinear sigma model on K3, there is no cancellation occurring in the elliptic genus. So what you see is what you get, essentially. However, there is a big disadvantage at really starting there to understand Mathieu Moonshine, because there are no known theory, which is explicit. So it's quite hard. On the other hand, if you have a non-generic theory, we actually know classes of such theories, and one of them is the so-called Z2 or before conformal free theory class. And a good thing about this class is that if you calculate the spectrum of generic states, it's the same for all these theories in that class. But of course, we have the complication of the cancellation. So the fact that there are no cancellation in the generic case was already pointed out by Kathrin in 2017 in a nice paper that she wrote there. And also there is a related paper by Song in the same year, treating basically the same ideas from, so Song is a mathematician, Kathrin is maybe a mathematician, but right, I understand better what she says than what Song says. Right, so a little bit of notations that we will need later. So the BPS states live, so the ones that are accounted for by the elliptic genus are living in a space that I call curly or calligraphic H here. It's a graded space, and at each grade, which is each level, as I call them, we have a space of n=4 superconformal states, the transform and the n=4. And these Hn here are actually representation or dimensions of representations of M24. So that's the way it works. And what I've just tried to explain with generic and non-generic is that what you see in the elliptic genus is a smaller space in general from what the full space of quarter BPS states is in the K3 theory. Right, so to give you an example, well, I mean, that's the example of the Z2 or before that I'm going to stick with in this talk. You see that in the elliptic genus, you see 90 states at level 1, 462 states at level 2, and so on and so forth. And the full number of states in these theories is 102 at level 1, and so on, you see. So there are 12 states there that actually are 6 bosons and 6 fermions, and because they come with opposite signs, they disappear from the counting. So that's the way it works. So I introduce the space H plus, calligraphic H plus here, to measure the discrepancy between the HPPS and the full number of states here. So the question that we ask is, what is driving this cancellation? Because these elliptic genus is actually just, roughly speaking, counting states without really it's too coarse, let's put it like this, to really get good information on the states that are actually cancelling and which one are staying. So we wanted to refine a little bit the information from the elliptic genus here in several ways, and that's what follows here. So in order to do this, we concentrated on Z2 orbifolds, superconformal field theories. And there is actually, well, I'll say a little bit more about it, but to start with, I should highlight the fact that the construction of these theories is rooted in the Kummer construction of K3 surfaces. So what do you do in a Kummer construction? You take a complex two-dimensional torus, which, as you see here, is obtained as the quotient by a lattice of rank 4. And then you mod it by a symmetry, which is Z2. And this would give you a singular, let's say, surface. And then you resolve the singularities in a minimal way there in order to obtain a K3 surface. And the conformal field theory that actually is induced by this is the one that I'm describing extremely rapidly here. So when we have an orbifold, this is a very old story, you start with the conformal field theory on the torus, and then you mod by Z2, and therefore you keep only in the untwisted sector the states that are invariant under Z2. But in doing so, you lose the modular invariance of your partition function, and therefore you have to add sectors, which are called twisted sectors, in order to recover the full modular invariance of the theory. All right, so this has been exploited in many papers over the years. So we look at this Z2 orbifold, and we are concentrating on a specialization here of the partition function that I didn't write for you here. It's not important at this stage. We take the specialization here in the Neveu-Schwarz sector. Okay, so before I was talking about the Raman sector at some point, but with the spectral flow, right? So this allows you, this kind of shift in the variable here allows you to go to the Neveu-Schwarz sector, and I drop the CFT here because by now we know, and therefore this specialization of the partition function is given by an object that I call ENS, and the Q bar minus 1/4 is actually inherited from the anti-holomorphic part of the partition function. Now this function, E of an S, can be written, of course, in terms of, let's say, functions, which here I've called U1/2 and U0 and T0. We've borrowed the notation from a paper by Gabadil, Keller, and Paul in 2017, but it's basically counting the states in this partition function after the projection here. And in terms of the mathematics behind, they are given in terms of theta functions and Dedekind eta functions. So pretty tame. Right. Now this beautiful object, as I said, can be completely messed up by the decomposition in n equals 4 characters. So that's the way it looks. As before, we had the function a of tau before, and now I can trace exactly the contribution to a of tau that come from the untwisted sector in red and the twisted sector here in blue. Now there's a 16 there. Now there's no magic there. This 16 is actually coming from the fact that there are 16 singular point or fixed point of this torus quotiented by Z2 when in the Kummer construction. So that's linked. And what we want to do with this is that we want to refine a little bit our understanding of this sector here, A of tau. So we already know in this K3 theory that some are twisted and some are untwisted, but we want to know a little bit more. So we are going to use insight from supersymmetry surfing or symmetry surfing. I don't know why I put supersymmetry there. It's just a symmetry surfing program to discriminate among these quarter BPS states in the twisted sector. And in a second step, we're going to use free fermions and their bosonic partners and subject them to a global SU2 action that is not as ad hoc as you could think, but to construct the quarter BPS states and give them a little bit more characteristic, if you want, what we have at the moment. Right. So step one, insight from symmetry surfing program. So I already said that Kummer surfaces can be viewed, their construction can be viewed in parallel with what happens in the Z2 orbifold. So you know already about the first entry there. The 16 fixed point, I said as well, that are parameterized by or labeled by the hypercube F2 to the 4, correspond to 16 linear independent twisted ground states in the conformal field theory. And the symmetry group of geometric symmetries of the K3 surface X, which is constructed here, I'm going to call it G sub X, okay? And it's induced by the underlying torus, and each different K3 surface, a K3 theory will have a different geometric group. And this GX permutes the fixed points. In the conformal field theory, right, you also have a group of symmetries, not surprisingly induced by the underlying conformal field theory for the torus, and this group permutes the twisted ground states. However, a well-known construction of adding the 16 twisting ground states with weight 1 for each of the terms here, and I call this combination alpha diagonal, okay, will be invariant under the G sub X action, right? And this, of course, was inspired by the fact that in the Kummer construction, there is a vector, which is again the sum of all these objects EA. We don't need to know exactly what they are at the moment, but this vector here is also invariant under the group GX. And this plays an important role in the symmetry surfing program, which would be a completely different talk, of course, because it's quite intricate. But let's say that what's important here is that we have discovered that there is an action of a group, which is called the octet group here, which gathers all the generators of all the geometric groups of K3 theories here. So there's a construction there, and it's quite complicated, but it's also quite nice. And this group that we obtain here in the symmetry surfing program is a maximal subgroup of M24. So, and it's not in M23, by the way. So it's quite a good group to have some information on. And it turns out that the diagonal state here is invariant not only in the GX, but because of the way we constructed the octet group there, it's called, it's also invariant under this octet group. And therefore it means that if we look at the orthogonal complement of that state in the 16-dimensional space of twisted ground states, then there should be a closed action of the G octet group under that space, right? And that's exactly what we did in 2015, is that we constructed very explicitly all these states, and inspired by construction of the 45-dimensional representation of Mathieu 24 by Margolin, we were lucky in a way that his construction was basically applicable almost effortlessly to our setup, and we could show that we had an action of the octet group on this 45-dimensional space here at level 1. So that was, well, we were very pleased with this. Of course, it's a beginning because it's only at level 1. So therefore, it was important to see if this, let's say, phenomenon would persist at higher level. So for this, we could introduce H-perp, a new space there, made of all the massive ground states in the Fock space over this orthogonal complement A, and make now an ansatz where now the space HBPS that we had before, accounted, where the states are accounted for by the elliptic genus, is now split into this H-perp and another piece that is called H the rest of the states within the counting of the elliptic genus, okay? So this ansatz was also made by Gabardine, Keller, and Paul, right? And the beautiful result, well, one of the beautiful results of their paper is that they were able to show that the octet group that we had before actually acts on H-perp and H-rest at all levels. So this was some encouragement that the symmetry surfing program is not completely doomed yet, right? But of course, that's not enough. And we need to know more about higher levels. And by the way, nobody has constructed these H-rest and H-perp at higher levels. So this is something to think about. Kathrin, in her paper that I mentioned before, also said that under deformation to generic K3 theories, then all the quarter BPS states accounted for by one part of the untwisted sector of the elliptic genus are lifted, meaning that they lose their status of quarter BPS states, so they are not in short representation anymore. They become part of a long representation with some partners. And the idea is, where are these partners coming from in the space that we are looking at? So at level 1, there is another nice result that was given to us by Keller and Zardet in 2019, is that they did a quite heroic calculation of deformation of conformal field theory by some marginal operators. So they switched on some moduli, and it's a second order calculation, it turns out to be, so quite involved. And they showed that if we deform the K3 theory along this diagonal direction there, all the states that are at level 1, that's the H1, in H1 perp, remain BPS, while those in H1 plus, so in this piece here, don't. So this is a very concrete calculation. At level 1, the situation is not the most general you can have, because H1 rest, there is no rest, it's 0. It just happens to be like this. So actually, again, it would be nice to do a calculation like this at level 2, but it's a bit complicated, of course, technically. So here's just a little cartoon that shows you that in the space of K3, I think of it as K3 surfaces here, but think of the K3 theories as well. It's the same idea. And we have the Kummer K3 surfaces here with the GX group. So for each such surface, you have a geometric symmetry group that we introduced before, and some of them as maximal symmetry. And they correspond to lattices when you build up your torus at C2 over lambda. And it depends on the shape of that torus, which could be triangular, square, or tetrahedral, right? And actually the symmetry surfing idea was actually gathering the symmetries of these 3 groups and cook up this maximal subgroup of M24, right? Now the arrows here are meant to represent, of course, the cartoon, deformation away from the Kummer point. So now the little arrows here actually are deformation along the moduli in the untwisted sector. And these ones actually just change the shape of the torus, but you stay in the class of Kummer K3. But then you have other moduli against which you can deform. And these ones come from the twisted sector. And the diagonal one that I talked about before is one of them, but there are other ones as well. Okay, so I could say more about this, but I think that given the time, I will press on.
Yeah, you have roughly 10 minutes.
Yes, exactly, I see that. So in terms of the functions B, C, and D, which are more concrete to work with, we have this correspondence between the spaces and actually the numbers of states, or the dimensions of these states. So the fact that I have the 16 here, which is now split into 15 and 1, is due to this diagonal direction, which is special. And then I have organized things to give you the number of states in H perp, the number of states in H rest, and the number of states in H plus, in terms of the twisted and the untwisted sectors. Now you see that in black here, I have a minus 2bn and a plus 2bn, because I know that in H plus, all the states, when I count them with signs, should cancel. So here, I'm not counting them with signs, I'm counting all the states, quarter BPS states, so it's a plus sign for the moment here. But what we don't know is whether you subtract all of the 2bn's from dn, all the 2bn's from cn, or a little bit from cn and a little bit of dn. And actually, just in case I don't go completely to the end, the net result of our investigation is that actually everything comes from this twisted sector, dn. So this untwisted states that come from the untwisted sector don't contribute to the cancellation, therefore they are generic. So that's the punchline, really. Right. So I've already answered that question. And in order to really come to this conclusion, what we had to do is dig a little bit into the free field representation theory of our algebra, n equals 4, and also by looking at the shape, the mathematical shape of the elliptic genus, with the information that we had there, we could construct explicitly all the states of interest thanks to these free fermions and free bosons. All right. So this is a little bit more technical, of course. I gave you here what the generators of the n equals 4 algebras are looking at in this free field representation. we have two so-called Dirac fermions and their conjugates, chi, and then we have the bosonic superpartners. Now, the reason why you even have such a representation can be viewed as being rooted in the fact that these J's here correspond to translation along the 4 direction of your torus, right? So all this, as I said, is terribly entangled with the geometry, and it's quite beautiful. So what we do next is that, so this representation has been known for a long time, but what we did is that we subjected these fermions and bosons to the action of a new global SU2. So if you look at them carefully, you know already that they transform into the SU2 affine, which is part of the n equals 4. So that again was known for a long time. And now we add an action of an SU2. Now this SU2 is actually not a random one. It's meant to be the SU2 that contains the linear part of the geometric groups that we saw in the discussion of the symmetry surfing earlier. Yeah, so that's linked to that. And that action of SU2 has to commute with the n equals 4 superconformal algebra, because we saw that M24 actually is completely acting independently of n equals 4. And because of that, we have a new quantum number to add to the game. And this allows us to differentiate more the states and see a little bit, trace where the cancellation might be. Right. And as I said, the SU2 geometric, as we call it, this new group, contains the linear part of the geometric symmetric group of the Z2 orbifold conformal field theory on K3 that we are interested in. And I've summarized here the action of the holomorphic and the anti-holomorphic action on the space of interest. So remember, H rest plus H plus, those that should cancel, and here those where we don't know if the states come from the twisted or the untwisted sector, right? So these chi's and j's transform as doublet under SU2 geometric and singlets under the anti-holomorphic part, and vice versa for the anti-holomorphic fields. The vacuum state and the diagonal twisted ground state H alpha diagonal transform as singlet under this group. Okay, and that's a little summary of the J3 eigenvalue of these fields. All right, and here we see that under the SU2, the J's are singlets. Okay, and here they are doublets. And under the SU2 geometric, as I said there, they transform, these two transform as doublets and so on there. So that's the rule of the game. And when you do this, you go on and you calculate intensely. And this was done mostly in Stony Brook at the Simon Center in the spring of 2019. And one member of the audience was sharing an office with us. So he knows exactly probably how much we suffered over the exact calculations of these states, but we did it for level 2, right? So what we did is we managed to write the states that populate these spaces, tracing the SU2 geometric signature. And what we found is that in the untwisted sector that Kathrin told us should be lifted, so shouldn't be generic, we only have one singlet of SU2 geometric. Now the numbers in black are the total number of states at that level in that sector. And what I have here in purple, okay, in the first line, how they decompose into SU2 representations. So here, for example, for the twisted sector, we have two singlets. That's the upper two means the multiplicity of the singlet. We have two triplets and we have four quintet. Okay, and we have full details about that. And what we know is that the cancellation so the states which are in Dn, so sorry, I should say it in another way. We know that the Bn's should be lifted, and there is a factor 2, if you remember, in this expression of A tau. There's minus 2Bn plus Dn plus Cn. So we have two singlets here, as far as the SU2 geometric is concerned. And we see that we have two singlets for Dn. So these seem to be ideal for pairing, right? So and in the untwisted sector Cn there, the representations have half integer spin. Therefore, if we believe that this is what governs the cancellation, then of course you can pick them up from that sector. And the story goes on because we had the partition functions, so not the states explicitly, but the partition functions we have. We were able to make an expansion for levels up to 100, I think. And each time we see that we have exactly the material we want in Dn in order to cancel twice Bn. So twice a triplet here, twice a triplet here. So 3 times size, so we need 6 quintet, we have the 6 quintet. So it's not a proof, of course, because it's order by order, but it certainly leads us to postulate that the states in excess in H plus are paired up according to their transformation properties of SU2 geometric cross SU2 bar geometric. Okay, and all the untwisted states accounted for by the untwisted sector UL, so the CNs here are generic. So this is a
really need to ask you to wrap up.
Yes, and I'm wrapping up. That here we have my little question to the audience is that our postulate relies on a positivity condition. Okay, and okay, you can ask me more later on. But we have tried to solve this positivity in generals to have an analytic proof, but failed. And my last page is just a summary of all what I've said, so I don't need necessarily to repeat. But even if this has nothing to do with Mathieu Moonshine, it's still interesting probably in understanding the generic properties of K3 theory. So thank you very much.
Thank you, Anne. So I'm afraid we've eaten into the discussion time as well, and I would like to transfer questions into the breakout rooms later on today, because that's what we've done all the time. Now we'll take a quick break in order to set up the talks of the second session this morning or afternoon, wherever you are. But let's thank Anne first of all, once again.
Okay. I believe we're recording now, and it's a pleasure to introduce Nils, who is going to tell us about holomorphic vertex algebras of central 24.
Okay. Yeah, first of all, I want to thank the organizers for the opportunity to speak at this conference, and of course also for organizing this workshop. So I will speak about holomorphic vertex operator algebras of central charge 24, more precisely about their classification. And before I start, I should say that most of the results here are joint work together with Sven Möller, or some of the results which I show here are joint work with Sven Möller. Some results are from other people. Okay, so let us start. So we will start with a short introduction where I recall Schelliken's classification of the unimodular positive definite even lattices in rank 24. So yeah, so this is a this will be the main, or this was the Niemeyer's classification was the main motivation for my research over the last years, and it's also the motivation for many other people working in vertex operator algebras. So we start with that. Then I will explain how Schelikens and many other people classified holomorphic vertex operator algebras of central charge 24. Then I say a few words about orbifold theory, a dimension formula for orbifolds, and introduce generalized dipoles to you. So we have seen, or we have heard a lot about black holes. Today we will hear something about dipoles. Then I remind you about some facts from the Leech lattice. And at the end, I will describe what is known about these generalized dipoles and how they can be used to classify vertex operator algebras geometrically. Okay, oops. Then let us start with Niemeyer's theorem. In 1973, Niemeyer showed that up to isomorphism, there are exactly 24 positive definite even unimodular lattices of rank 24. And such a lattice is uniquely determined by its root sublattice L2. So the root sublattice is just the sublattice generated by the vectors of length 2 in L. That's the sublattice of L. And this root sublattice L2, that's an orthogonal sum of lattices of type ADE. And you can see the corresponding Dünken diagrams below, AD and then E6, E7, and E8 on the right. And so you can, in this way, you can associate to your Niemeyer lattice such a Dünken diagram. And this diagram classifies your lattice uniquely. So it's a very beautiful theorem. And there are at least 5 different proofs of this result. And let me shortly describe them. Niemeyer proved this result originally using Kneser's neighbor method. So what does that mean? How does it work? You fix some prime, and then you take any lattice in the above genus, and you calculate the p neighbors. And from these p neighbors, you calculate again the p neighbors again and again. And after some time, you won't find any new lattices anymore. And then you have found all your lattices in the genus. Yeah, that's because we know that the neighborhood graph is connected. So in this way, you can find all the lattices in your genus, and this is a method which was used by Niemeyer. So this is the first proof. Then Wenkow found a very nice proof using theta functions with harmonic coefficients. Yeah, the main idea here is maybe that you find a relation between vectors in your lattice and vectors in the ambient space using theta functions. So that's a very beautiful proof. Then there's a proof which is less well known, and it goes as follows. Well, the main idea is you can classify the dipoles in the Leech lattice and thereby classify the Niemeyer lattices. So this is something which I will describe later in the talk when we come to the Leech lattice. And then there's a fourth proof which uses the Minkowski-Siegel mass formula. The idea here is that the sum over the inverses of the orders of the orthogonal groups of the lattices in a genus is a fixed number which is well known. That means you can check whether a list of lattices describes your full genus by just summing up these numbers, and when you get the right number, then you know that you have found all isomorphism classes. This is maybe the simplest proof. On the other hand, you have to come up with the Minkowski-Siegel mass formula, which is a quite smart formula in my opinion. Then there is another sophisticated proof which uses the classification of automorphic representations of O24. And I won't say much about this, except from that you can find this in the book by Chenevier and Lann, which is called Automorphic Forms and Even Unimodular Lattices. So these are the different proofs of Niemeyer's theorem, which are known. And this is a motivation for a lot of research in VOA theory. And yeah, we want to see that the classification of vertex operator algebras that we have at the moment, which is similar to the second proof, it's a bit similar to Venkov's approach. So we will see in this talk that we can have a proof probably which is similar to the classification of the dipoles in the Leech lattice. This is what I will explain. In my talk. Another reason why we started with lattices is that the theory of vertex operator algebras is in many aspects similar to the theory of lattices, but there are also some important differences, as we will see. Okay, and maybe just in case you don't know what a vertex algebra or vertex operator algebra is, don't worry, I prepared a slide for you. So usually people say it's difficult to describe what a vertex operator algebra is. Personally, I don't think so. So yeah, what is a vertex operator algebra? That's just a graded vector space together with a state field correspondence, which associates to each state, that means to each element in your vector space, a field. And this field is just this field has a Laurent expansion, and the coefficients are just linear maps on your vector space. Okay, so here you have the state in your vector space. This is some element in V, and you associate to this state a bunch of linear maps, and you organize them in these vertex operators. And of course, the state field correspondence has to satisfy certain axioms. And in addition to that, we have an action of the Virasoro algebra on this vector space. And the grading of V is just the grading by the L0 of the Virasoro algebra. Okay, so, and what we will do in this talk is we will study the classification of holomorphic vertex operator algebras, namely of central charge 24. So what does holomorphic mean? Holomorphic means these vertex operator algebras have only one module, namely itself, plus some additional regularity conditions which are not important for the purpose of this talk. And the central charge is the action of the number by which the central element of the Virasoro algebra acts. So these vertex operator algebras, the holomorphic ones of central charge 24, these are the analogs of the positive definite even unimodular lattices in rank 24. Okay, and these vertex operator algebras have been classified, or almost have been classified, by the work of Scheithauer and many other people. And yeah, I want to quickly recall this classification, which is usually named Scheithauer's list. And the idea of the classification, yeah, I think it's easy to understand. So we start with our vertex operator algebra of central charge 24. We assume that it is holomorphic. That means it has only one irreducible module, namely itself. Then we can look at its V1 subspace. And this subspace is actually a Lie algebra. The question is, what is the product? For this, I go back one slide. So you can think of a vertex operator algebra also as a vector space with infinitely many products. These products A and B. Okay, and we take the zeros product. Here, so our V1 is a Lie algebra under the zeros product. And this Lie algebra is reductive. More precisely, in this case, we know automatically it's either 0 or it's abelian of dimension 24 or semi-simple of rank at most 24. These are the three possibilities that we have. And yeah, let us consider the last possibility, the third possibility, that our V1 is semi-simple. then we can write down the character of this vertex operator algebra. And by character, I mean our character takes the following form. So we have two variables. One is a tau variable, which measures the L0 eigenvalue. And then we have also the Z variable, which lives in a Kathrin of V1. So V1 is semi-simple. We choose some Kathrin algebra. Then Z lives in this algebra, and Z acts naturally in its zero mode on V, and we can calculate the corresponding trace. This is a character of V, and by the work of Chu, we know that this character is actually Jacobi form of lattice index. So here is the first appearance of, or the second appearance of modular forms. So from this fact that this is a Jacobi form of lattice index, Schelikens derived 7 trace identities. Yeah, I won't write them down here explicitly, but you can derive 7 trace identities from this. And then you can put these identities on a computer, and after several weeks, the computer gives you 69 solutions. That means you have at most 69 solutions for your V1. Okay, and Schelikens now conjectured that each of these possibilities is realized by a unique vertex operator algebra. That's what he conjectured, and this was in 1993. So roughly 20, or exactly 20 years after Niemeyer's result. And it took mathematicians quite long to prove this conjecture. So roughly 2 years ago, the proof of the following theorem was completed. So we look at the holomorphic vertex operator algebras where the V1 space is non-trivial. Yeah, this case is completely solved. So there we have the 69 cases from before. And in addition, we have the case where V1 is abelian of dimension 24. So these 2 cases are settled. The case which is not settled is the case where V1 is just 0. So up to isomorphism, there are exactly 70 holomorphic vertex operator algebras of central charge 24, which have non-trivial V1. And such a vertex operator algebra is uniquely determined by its V1 structure. Okay, so this is the analog of Niemeyer's classification, and it combines the work of many, many people. And the proof is roughly, was finished 2 years ago. The case that V1 is trivial, that's the uniqueness of the Moonshine module, or the FLM conjecture. This case is still open, but the other case is now solved. Okay, so this is Schelikens' list. Anything more that I want to say on this? No. Okay, so now you know how Schelikens, how vertex operator algebras are classified. So the proof, the idea of the proof is in some sense similar to Wenckow's classification of the Niemeyer lattices. Okay, then let us see what orbifolding is, the dimension formula, and what generalized dipoles are. So yeah, we have seen how we can classify vertex operator algebras of central charge 24. Now we want to see how we can construct them. And one important construction is orbifolding, or orbifold theory, and this goes as follows. So we take a holomorphic vertex operator algebra of central charge C. Then V is holomorphic, then the C must be a multiple of 8. So similar to the lattice case. So when you have a positive definite even unimodular lattice, then you know that the rank must be multiple of 8, and we have the same result here. So you take such a holomorphic vertex operator algebra, and we impose no restriction on the central charge at the moment. And we take some automorphism of finite order. And we also have to assume type 0, which I just wrote down to make the statement completely correct. So, so we take some automorphism of finite order. And we have one additional condition. So for each power of G, there's a so-called twisted module. And you have to assume that the conformal weight of these modules are positive for J different to 0. So when this is satisfied, then the fixed points of V under G, so this fixed point space here, this is again a vertex operator algebra, but this is no longer holomorphic. So this has more than one module, namely exactly n squared irreducible modules. And you can easily construct them as subspaces of these twisted modules. The idea is the following. So you have your twisted modules, and these modules carry an action, or G acts on these twisted modules, and you look at the eigenspaces. Yeah, when you decompose the twisted modules into eigenspaces under the action of G, yeah, and then you get these spaces W, J, K. This is how I call them. And now when you get, now you add certain modules of VG to VG to get a new bigger vertex operator algebra. And this bigger vertex operator algebra is now again holomorphic. So essentially what you do is you add to VG the fixed points of the twisted modules under G. Okay, this is the so-called orbifold of G. And this is now again a holomorphic vertex operator algebra of central charge C. And the reason why we add these twisted modules to our fixed points is that we want to have something holomorphic. Yeah, of course, we could also study VG, the fixed points, but this would not be a holomorphic VOA. It would have many different modules. Okay, so now we know what the orbifold of a VOA is. So we can, starting from one VOA, then we have some automorphisms at hand, we can construct many new ones. And when you do this correctly, you can, in certain cases, construct all other vertex operator algebras. For example, this is the case in central charge 24. And this is one of the main subjects of this talk. Okay, then let me continue. Also, maybe I should say something more. The problem with these orbifolds is that they are difficult to study, because in general, we don't know much about these twisted modules except that they exist. So a question is, yeah, how can we get some information about these orbifolds? For example, an important invariant is the dimension of the V1 space. So what is the dimension of the V1 space? I give you an orbifold. What is the dimension of the V1 space? This is something that we can answer now.
Could I ask a question?
Yes, of course.
I think I missed the definition of type 0 on that slide.
Yeah, I didn't give it to you. So
I guess what I'm worried about is what in physics are called modular anomalies, that you can have something that looks like an automorphism, but when you actually try to construct the orbifold, there are phases that come in defining the group action and the twisted sector that lead to an inconsistent partition function.
Yeah, I think this is exactly this is why we impose the type 0 condition. So the
type 0 means type 0 is no modular anomalies.
So type 0 in a mathematical language means that the conformal weights of the irreducible modules take their values in 1 over n times the integers.
Okay.
And
I think that's called level matching in physics.
Okay, I'm as you can see
Okay.
from the unfancy version of my slides, I'm a mathematician. Yeah, so this is the condition that we impose, and then of course there are some ambiguities in. So what is, when you define your action on the action of the group generated by G on the twisted modules, there are some ambiguities. And what I say here, you can choose these actions such that the orbifold is a vertex operator algebra whose structure extends that of the fixed point algebra. Okay, you can make such a choice that everything is consistent. And for this, we need the type 0 condition.
Okay, thanks.
Okay. Okay, so now for the rest of the section, let us assume that the central charge is 24. And as I said, or as we know now, the dimension of the V1 space of a VOA is an interesting quantity, and it's not so easy to get to calculate it in general. And here's a nice formula which gives it to you very easily. And the theorem is as follows. So the dimension of the V1 space of your orbifold is obtained by adding to 24 the dimension of these fixed point spaces, and the coefficients C and D, they are determined by the system of linear equations, which I wrote down there. And then you have a correction term RG, which I could write down explicitly, which contains dimensions of twisted modules, which contains the dimensions of subspaces of twisted modules of weight smaller than 1. Okay, so there's an explicit formula for the RG, but I don't write it down here. And there are some simple conditions which imply that the RG actually vanishes. Okay, so this is the dimension of a V1 space. And the good thing is the quantities on the right-hand side are easy to determine because the twisted modules are not involved. So the dimensions that we need to determine the dimension of the V1 of the orbifolds are just obtained by calculating the action of the powers of G on your original VOA. Yeah, so this is the VOA you start with. You have a G action, so this here is easy to calculate. So this is no problem. This here can be difficult, but in general, there are some nice conditions which imply that this is 0. And in general, you can also calculate this rest term here. One important observation is that this rest term here is non-negative. So this here is an upper bound for the dimension. Yeah, so we have an upper bound for this dimension. This is important. And this upper bound is reached when the rest term vanishes. Okay, and I think I want to indicate the proof of this. Actually, this formula here is an abstraction coming from Eisenstein series. So we had Eisenstein series already several times at this conference. And yeah, here's another occasion. So how do you prove this dimension formula? So you take, you define the abelian group Z divided by NZ to the power of 2. And on this abelian group, you define a quadratic form in the way which I wrote down there. So it looks like a hyperbolic plane. Then you have what is called a discriminant form. Then we calculate the character of our fixed point algebra, more precisely the vector valued character. So VG, this VOA here has n squared modules. We calculate the character of all modules and put them into a big vector. Okay, so these are the characters of the individual modules. And yeah, we put them into a vector valued character. Then we actually get a modular form for the so-called Y representation. To be precise, it's a nearly holomorphic modular form of weight 0 for the Y representation. So it's holomorphic on the upper half plane, but it has a pole at infinity. So the character gives you a modular form for the Y representation. Now we construct another modular form by lifting this Eisenstein series, which I have written down here. So this small f is just an ordinary scalar valued Eisenstein series for gamma 0n. Okay, and there's a natural way to lift this modular form to a vector valued modular form for the Y representation. And this time we take the dual Y representation. So now we have two modular forms for two representations which are dual of each other. So we can contract or pair these two forms. Then we get a scalar valued modular form of weight 2. And by the residue theorem, we know that its constant term has to vanish. So then we just do the calculations, which is a bit easier to say than to do. And the result is the following. So we get the first dimension formula. So the dimension of the fixed points of G on V1 are related to the V1 spaces of the different orbifolds in this way here. So this is the first dimension formula we get from the pairing with the Eisenstein series. And now we take linear combinations of this equation for different powers of G, and then we get the desired formula. So if you want to phrase it very shortly, then you can say the dimension formula is an obstruction coming on the characters coming from the Eisenstein series. There are many other obstructions from other modular forms, not just from Eisenstein series. So you can do the other argument. You can do this argument with any other modular form for gamma 0n of weight 2. The problem is you will find expressions which are very difficult to control. So this function here gives you a very nice. This function gives you quantities that you have a chance to put your hands on. Okay, so now we can calculate the dimension of the V1 space of an orbifold, and this dimension is an important invariant for our VOAs. So next we want to define generalized dipoles, and I will explain the name a bit. The meaning of the name will become clear in a minute, but you see from this formula here, the case since 0 is the lower bound for RG, of course it should be interesting to look exactly at this bound. Or when you have such a bound, you can ask what happens if RG is 0. This is what we want to do. And we call our automorphism a generalized dipole. If this rest term vanishes, that means that the upper bound in the dimension formula is attained. And in addition, we make another assumption. We assume, so our V1, the V1 subspace of the fixed points. So the right-hand side here, this is the Lie algebra. This has a Cartan subalgebra. Or I should start here. So this, the V1 space of the orbifold is a Lie algebra, and it has a Cartan subalgebra. And we want that the Cartan subalgebra of this of the orbifold does not get contributions from the twisted modules. This is what we say here. Yeah, so the Cartan subalgebra of the orbifold does not get contributions from the twisted modules. That's the second condition that we impose. And the reason for this is that we then can control inverse orbifolding better. But that's not important. So we have these two conditions, which the first one, I think it's clear that you should look at this case, at the boundary case where the upper bound of the dimension is attained. And after some experimentation, you find that this is also a good idea to that this is all. Okay. And the next theorem stresses this. Okay. So this result also explains why generalized dipole is maybe a good name, because for the dipoles, they do what they should, or yeah, in some sense, they generalize the dipoles in the Leech lattice. So the next thing which you can show, which is analogous to Borchert's bijection between the dipoles and the Niemeyer lattices with roots, we have analogous statements for vertex operator algebras. Namely, we have a natural bijection between the dipoles, and now dipoles are automorphisms. So we have a bijection between the classes of dipoles in the automorphism group of the vertex algebra of the Leech lattice. And yeah, we have this, in addition, we have this rank condition. So we have a bijection between these dipoles corresponding, also with positive rank, and the holomorphic vertex operator algebras with non-trivial V1. Okay, so we have a natural bijection between these two objects. Okay. And yeah, the proof is based on an average version of Katz's very strange formula. So, and this is a completely abstract result, okay? And that means we can classify vertex operator algebras by classifying generalized dipoles. Only that the situation here is much more complicated, since yeah, the automorphism group of the lattice of the vertex algebra of the Leech lattice is of course an infinite group, and it's not so easy to determine the conjugacy classes. But this theorem is the basis for a geometric classification. Now, what have we done so far? We have shown that when you take any of the Lie algebras on Schelliken's list, then we write down a generalized dipole such that the corresponding orbifold gives this Lie algebra. Okay, so the point of this theorem is this theorem here is abstract, and this here, also this theorem, this theorem here doesn't prove the existence of any VOA. Yeah, it just says when you have one, then it corresponds to a dipole, but it doesn't prove the existence of any VOA. Here we uniformly prove the existence of 7 of the VOAs on Schelliken's list with non-trivial V1. Okay. So, and I have to add here at this point, this is not the first uniform construction of these VOAs. Another one was given by Höhn in 2017, which uses a completely different approach, which is based on coset theory. So in this way, we have a uniform constructions of the Lie algebras on Schelliken's list by generalized dipoles. What is interesting in this context here is we have a natural projection from the automorphism group of the vertex operator algebra of the Leech lattice to the orthogonal group of the Leech lattice. So there's a natural map. And yeah, the automorphism group of the Leech lattice has many conjugacy classes, roughly 160, and you hit only 11 of them when you project. So, and the classes which you get, they depend on the isomorphism class of the orbifold tensorized with the hyperbolic plane. So this is something, as I said, the theory of VOAs is in many aspects similar to the lattice case, but there are also important differences. When you take a Niemeyer lattice and add a hyperbolic plane, they all become isomorphic. That is not the case for VOAs. Okay, anyway, so then, yeah, maybe I come to my last slide. So, as I already said, the bijection between the generalized dipoles and the vertex operator algebras of central charge 24 with non-trivial V1, this allows to give a new classification of these VOAs. Oops. Just what do we have to do? We have to classify the conjugacy classes of dipoles. This is what we have to do to get a classification. So we already have shown that there is at least 70 classes. So the next step, what we have to do is that they are unique. And yeah, we are close to this, but it's not completely finished, but I'm confident that this will be possible. So, and how can we classify these classes? The idea is similar to Conway, Parker, and Sloan's idea to associate diagrams. So Conway, Parker, and Sloan associated Duncan diagrams to the deep holes, and we want to do something similar here. So one question is, where do we get the diagrams from? And the idea is as follows. So you take your automorphism, then you look at the fixed points under this automorphisms in your vertex algebra and take the corresponding V1 space. Yeah, that's, yeah, so you take this V1 space, this is a Lie algebra, then you take a Cartan subalgebra of the fixed points, and they act, so this Cartan algebra acts on the twisted module on the weight 1 subspace, and yeah, then you get weights from this action. And these weights actually form a Duncan diagram. This is something you can prove. And I think, or we think that these diagrams can be classified. So, and in this way, we get it, also, yeah, so these diagrams can be classified. And in this way, it seems that we get a geometric classification of at least of the generalized deep holes. Yeah, so you can associate a unique diagram to such a hole. And in this way, we get a geometric classification of the holomorphic VOAs of central charge 24. So
by the way, we're at the 9-minute mark for if we keep on schedule.
Okay, yeah, I think I will be finished in a minute.
Sure, go ahead.
Okay, so we haven't completely finished the calculations, but we are very close. So yeah, I'm optimistic that when we have the next conference next year, where we can hopefully meet in person and have no problems with the technique, then I can make these statements a theorem. Okay, so yeah, so this is maybe all I want to say. So the main points of my talk are you can classify the Niemeyer lattices by classifying deep holes in the Leech lattice. And it seems very probable, or we are very close to transferring this proof to VOAs. So we can classify VOAs of holomorphic VOAs of central charge 24 by classifying generalized deep holes in the automorphism group of the VOA of the Leech lattice. Okay, so this is what I wanted to say. Thank you very much.
Are there questions? Are there any questions?
Greg Moore raised his hand, Dan.
Okay, okay. Yes, go ahead, Greg.
Yeah, can all these vertex operators be defined over finite fields?
Yeah, you can. Yeah, I think you can do that. You can define them over the integers, and I think you can also define them sometimes over finite fields. Of course, yeah, yeah. Sometimes it's possible, yes.
All right, so I had a related question then. So what about 24n?
The problem, so our dimension formula does work very well in dimension 24. For 48 and others, you get contributions into your dimension formula where you have no control of. We tried that. So the case dimension 24 seems to be special, at least as far as we can say.
Do you think there are a finite number of automorphism of VOAs of central charge 48?
I would guess, also if I should make a guess, then I would say yes.
Thanks.
So, also what you can, yeah, but a proof would be certainly much more difficult. So so you could try to extend Schelicken's arguments to higher rank cases. In principle, you still get many restrictions from the fact that the character should be Jacobi form. But of course, this is speculation, but at least the modularity imposes strong restrictions, and that might be sufficient to prove finiteness. So if I should make a guess, I would say there are finitely many, but of course that's no proof. That's just a guess.
So I have a question, please.
Yes.
It's a rather general question. A lot of the background literature that you cited involve rather hefty computation.
Yes, that's correct.
Is your work just done by pure thought, or at some stage have you had resort to a computing device?
We used computers a lot as well. So yeah, we certainly also need computer computations. We need less computations than Schelicken's, but we also need them. So
can you indicate what sort of computations you're doing? I mean,
yes, I can.
It wasn't clear from your talk.
Yes, so for example, when you want to, I give two examples. So one is we wrote down an explicit list of 70 generalized dipoles, which give all the elements on Schelicken's list. And you can make some educated guesses, but it still was used try and error. And so we had to verify some cases, and we did this on a computer just to be quicker with verification.
I mean, I approve of the use of a computer, but it wasn't apparent in your talk that you ever needed one.
Yeah, it is, so we can almost, I think we can almost avoid it. So, I mean, we can just write down the dipoles and no computations are anymore necessary. This is something we can do, and but we use the computer to find these dipoles. Of course, when you have them, then you can do the calculations almost by hand. What you have to do sometimes, you have to verify that some characters do what you want. And for this, we had to calculate some theta, we had to calculate the theta functions of certain lattices. That's what we use the computer for example. In the verification that the 70 elements give the right Lie algebras. So yeah, I didn't make this very explicit, but at this point, yeah, we used computers to calculate theta functions, and we will also need them. So we classified the generalized dipoles in the automorphism group of the Leech lattice VOA to a large extent. As I said, we are almost done. And in this classification, we also used the computer. And this is, when you look at Conway and Sloan's and Parker's classification of the dipoles in the Leech lattice, they do it by hand. But when you look at the calculations, then you see, also I would do it with a computer. So these are the two places. So I think, yeah, at least for the classification of dipoles, we will use computer calculations.
So I'd like to point out that we can continue the question and answer in the breakout rooms, and it's almost time for the next talk. So we might have time for one quick question, but otherwise maybe we should continue this after the next lecture. Nils, will you be here for the breakout session?
Yeah, I will be there for some time myself.
Let's see. So